This session is session number 11 about overlaying spectra. When we overlay spectra, we can often see subtle differences between materials that are very similar or have only slight differences in processes, different temperatures, different chemical treatments, different degrees of oxidation. So an overlay mode can be very valuable. We'll start off with putting the native hafnium oxide as the base peak, or the base spectrum. We are just going to make a simple overlay with a max. We're going to maximize the peak height for all three spectra. We're going to overlay the native silicon oxide on top of it, and then we're going to overlay the native zirconium oxide on top of it. All three of these are native oxides. None of these three require any charge correction, but yet you still see that there's a reasonable difference in the binding energy of each of these peaks. Silicon is about 286, whereas normally we expect it at 285. The black one is hafnium oxide. It appears at 286.2. There is a reason for these differences. The reason is that surface dipole moments of highly polarized materials has a bias that affects just the carbon, which is at the very top of the overlayer system. That's some physics that would require a special training lesson. So this is one way we can make an overlay, and we can zoom in on it in various manners, whatever is appropriate for your needs. That's one example of overlaying. We're going to close that for now. Now we're going to switch from carbon. Let's go to oxygen. I'm changing each of the spectra to find the oxygen region by looking at the binding energy. We're going to do the same thing. We're going to overlay the oxygen, and this time we're going to choose to overlay. No, we're just going to do a normal maximization overlay. So we're going to start with this native oxide. Choose the overlay button. Max peak height. We'll go for the zirconium oxide next, make the overlay. Then we'll go for the hafnium, make the overlay, expand it to see everything. You can see clearly that the native silicon oxide has an oxygen out here. It's about 533. And the blue one, which is zirconium, has a peak at about 531. It's possible that you can see peaks all the way down to 529 for the oxygen chemical shift. This information can be used to study the ionicity or the polarization nature of these different native oxides. So that's another example of how we can make an overlay. Let's use a different approach. Sometimes we want to normalize at a particular energy, and that would be the case where we've got a metal and a metal oxide, and there's a slight variance in the position of the metal. But we're going to use these data sets to demonstrate that capability. Start with the zirconium, normalize. So this time we're going to normalize at 532 eV. Let's make it 532.5 eV. Okay, so now all the other spectra will be normalized at that particular energy. Zirconium. I'm sorry, we've got zirconium there. Now we'll do hafnium. Okay, and then we'll do the silicon oxide. Okay, here at 532, right up that crossover point, that's where we have decided to do the normalization. That's about it for this basic overlaying of spectra presentation. Thank you.